Now we come to possibly the most important aspect of simple harmonic motion, and that is finding omega, i.e. the angular frequency, in terms of physical variables. Variables of our system, what our system consists of. We need to be able to predict what the angular frequency is going to be. So we started all off with the fact that A, for simple harmonic motion, the acceleration will always be equal to negative omega squared times x. So we need to, this is A in terms of x right here, and this is what we basically need to start our derivation with, this whole concept. If you can figure out what this constant is right there that relates the acceleration and the displacement, you've got negative omega squared, you've got omega, you can figure out the angular frequency in terms of physical variables. Let's start with the most simple version of this, and that is our spring mass system. In our spring mass system, we have a displacement x, and then the force is going to be negative kx. So this is the force due to the spring is F sub s, and that, because of Hooke's law, we know will be negative k times the displacement x. Well, if the spring is the only force, then that means that the force of the spring will be m times a due to Newton's second law. So m times a will equal negative kx. Well, how do we just solve for the acceleration right here? What do we get? Negative k over m times x. So that tells us right away that if this is an equation for simple harmonic motion in which a is equal to negative omega squared times x, what is omega squared? Well, just look at this. It's whatever is multiplied, negative something multiplied by x, omega squared must be k over m. Omega squared is going to be the k over m for this spring mass system, and therefore omega, the angular frequency, will equal the square root of k over m. So this is really important because what this tells us is that the frequency of a spring and mass system depends on two things. It depends on k. The higher the spring constant, the faster this goes back and forth. And it also depends on m. But if I increase m, what will happen to the frequency? The bigger the mass, the slower it's going to go back and forth. Let's just demonstrate this with our little oscillator here. I've got the mass set at 600 grams here. I'm going to pull this down so my amplitude is 3 of these blocks, and I'm going to release it. And you can see the frequency is like 1 and 2 and 3 and 4. So now what I'm going to do is I'm going to change the mass by reducing it. Let's go ahead and change the mass. Now watch what happens to our equilibrium point as I reduce the mass. Yeah, it makes sense the equilibrium point goes up because gravity's not pulling as hard. But I'm going to still pull it down the same amplitude. Watch what happens to the frequency now. 1 and 2 and 3 and 4. Let's go ahead and compare those two side by side so you can see that the less mass there is, the faster this thing moves up and down, the higher the frequency. Let's take a look at another example where I just increased the k. Check out this one. Same mass, higher k value, it goes faster. And that makes perfect sense because the greater the k, the greater the force, hence the greater the acceleration. So this makes perfect sense that the angular frequency for a spring mass system is the square root of k over m. Now, what's great is that the omega, the angular frequency, will always be the square root of something over something. Every single time it'll be the square root of something over something. So let's go ahead and predict what omega will be for a torsional pendulum is something like this. So this is it's a torsional spring, meaning that it's something that will exert a known torque when you rotate it by an angle theta. So I'm going to rotate that by an angle theta. So rotate that, and there we go. Here's our torsional pendulum. And it goes back the other way after it reaches its amplitude. It goes back the other way. Now, what is this going to be? This is one of these situations where the analogies really, really help. So instead of square root of k over m, instead of k, the torsional spring constant is called kappa. And that is the ratio between, just like the force of a spring equals negative kx. So for a torsional spring, the torque due to the spring is equal to negative kappa, it's a Greek letter kappa, times what? Instead of x, what's the analogy? Times theta. So now we got to use our analogy to figure it out. What is it going to be for a torsional spring? Omega will equal, it's always the square root of something. What over what? Well, let's just use the analogy. What's analogous to k? It is kappa, Greek letter kappa. What's analogous to mass? The moment of inertia, or the rotational inertia. So for a torsional pendulum, omega, the angular frequency, is kappa, square root of kappa over I, the moment of inertia. We can play this game with a whole lot of other stuff, including a physical pendulum. Now, physical pendulum is a little bit tougher because for a physical pendulum, what you have is any object can be a physical pendulum. Here's a spoon, physical pendulum. Here's a meter stick, a physical pendulum. Any object you grab, doesn't matter what it is, even this lid can be a physical pendulum if I go back and forth like this. Any object can be a physical pendulum. So the trick is to figure out what is going to make the physical pendulum oscillate faster and what's going to make it oscillate slower. This is not as easy for a physical pendulum, but you can use a little mnemonic that I like to use. So when you're playing with physical pendulums, back and forth, any object like this, ow, you got to watch out. Because with a physical pendulum, you might get some damage over your eye. So I like to write this like this, square root of dmg over I. Got to watch out with those physical pendula. You might get some damage over your eye. What the heck does this mean? D is the distance from the axis of rotation to the center of mass of the object. So if we have an axis right here, there's our axis of rotation, here's the center of mass, D is the distance. Now, you could also replace that with what variable, that is the displacement from the axis of rotation to the point of force application. In this case, the force is mg, the force of gravity. What do we usually use for that? Displacement from axis of rotation to point of force application, where gravity is being exerted. We usually call that R. But then this mnemonic will not work if you do that. But it's still useful. So square root of damage over I will give you the angular frequency of a physical pendulum. Now, let's see if we can make sense why this is so. Well, mg times d, the greater that mg times d is, mg is the force, d is the R value, the greater these things are, the greater the torque. That's why these are on top and I is on the bottom, because the greater the moment of inertia, the harder it is to accelerate angularly. It'll slow it down. It'll be lower frequency. So for a physical pendulum, the angular frequency is, it's always the square root of something, it's always the square root of something over something, and it's damage over your eye is the best way, little mnemonic that I can use. Now you can find, now that you have omega, you can find the period, and these are often given to you, but you have to derive it as well. So notice that you can find the period just using omega is equal to 2 pi over t. use that. The reason I prefer to just memorize omega, because it's always the square root of something over something 100% of the time. And then you don't have to remember that 2 pi constant. Once you memorize the omega values or figure them out, making sure they make sense physically, then you can solve for the period. For the period of a spring mass system, it's 2 pi times the square root of m over k. Notice the k and the m are reversed because the period is inverse. Period you can solve by 2 pi over omega. So that's 2 pi times 1 over omega, which is that. And for a pendulum, it's this, and we're going to derive that in just a minute. One thing that I want you to notice that is conspicuously absent from the angular frequency equation is the following. Let's go ahead and what I'm going to do is I'm just going to displace this 1 unit. Okay, so my amplitude is now 1 unit. I'm going to let this thing go. And let's go ahead and I'm going to time the period. So the best way to time the period of a pendulum or a simple harmonic oscillator of any kind is to really start the time when it crosses this middle line and then time 10 cycles. So I'm going to go ahead and do that. And here we go. Start. 0. And there's 1 and 2 and 3 and 4 and 5 and 6, 7 and 8 and 9 and stop. So I got 18.28 seconds for 10 periods. That means the period of this thing is 1.828 seconds. This time I'm going to pull it down to 3. I'm going to triple the amplitude. And I'm going to watch, see, it seems to be moving a lot faster. Let's go ahead and time this 10 cycles. When I press start, when it crosses the middle, and the reason that it's best to do that is because it spends the least time at the middle. If you do it at the ends, then it spends the most time there, so you actually get the biggest error. There's only one very brief moment when it crosses that, and I'm going to say 0 when it crosses. Here we go. And 0, 1, and 2, and 3, and 4, and 5, 6, 7, 8, 9, and stop. 18.2 again. Notice that within the uncertainty of the error of my timing, the period does not depend on what? It doesn't depend on the amplitude. I can pull this down as far as I want. I can pull it all the way down here. As far as it'll go, that's as far as it'll go. And I'm just going to time one of them here just to start and stop. And 1.82 again is the period. Doesn't matter what the amplitude is. For a spring mass system, the amplitude has no effect. The same is true for a pendulum, but for a pendulum, it's within limits. There is a limit with a pendulum, as we will find out.